test. That's reviewed, yes? Sharp turn, whether it be corner or cusp. This is the hardest part of the day, proving a derivative doesn't exist is the hard part of the day. We'll get to that on the back. See the back if you go back and study this. And then vertical tangent. Why would a derivative not exist when there's a vertical tangent? Think slope. The slope is rise over run, and if it's going vertical, then there is no run. There's no sideways. You division by 0. So vertical tangent is bad because the slope is division by 0. You with me? All right. You should be able to tell me, based on a graph, where continuity and differentiability succeed or fail. So let's go some people. Ian here, give me a point where the function is continuous but not differentiable.
I think it's -1.
-1, I agree. At x equal -1, there is a sharp turn. There is a second point. Let's say, let's get a gentleman here. Mr. Schwadberg, what's the second point where the function is continuous but not differentiable? 0, yes. What's the problem with 0? Yeah, there's a vertical tangent there and a cusp there, so there's the 2 points. Cool, check. At what value is the function not differentiable? Okay, so Tanya, give me a place where the function is not differentiable. Give me just one. -1, yeah. We just said it's not differentiable at -1. Give me another one. Let's go, Marina.
0.
0, yes. Going for the easy ones, good job. Okay, Aiden, give me another one where it's continuous, or sorry, not differentiable. 2, yeah, there's a discontinuity at 2. It can't be differentiable at a point that doesn't exist. That's ridiculous. And one more, Mr. Bushko. -2, yes, there's a discontinuity there. Are there any others besides those 4? That's all I see. Are you with me? Okay, cool. At what point is the function differentiable but not continuous? Where's the derivative exists, but it's not continuous there? Where's that at? Not possible. Okay? Draw yourself a Venn diagram here, and it goes like this. Differentiability is a subset of continuity. Now, given that Venn diagram, is it possible for something to be differential but not continuous? Surely not. So, this is not possible. True or false? Differentiability implies continuity. True. True or false? Continuity always implies differentiability. False. All right. Okay. Going on to then, try this multiple choice question here. The graph of the derivative is given, and which of these could be the original f function? Give that a go. ¿Listos? D? D? How do you say D? How do you say it? Any? Any? That's what it is. Okay. So, I feel like if you thought A or C, you definitely know some calculus. If you thought D, you know calculus, but you're easily confused. And if you thought B, then I don't know what you're thinking. You're just choosing an answer for some reason. I don't know why. So my thought process was this is linear-ish for the derivative. So f should be parabolic-ish. Yes? Do you agree? All right. For this, it feels like the derivative is parabola-ish, so the antiderivative should be cube-ish. Yes? And for this, it's negative linear-ish, so the antiderivative should be negative parabola-ish. In terms of those, which two satisfy those conditions? A and C have parabola, cube, parabola behavior, so it feels good there. Which do you choose, A or C, and why? It is A. Why? Yes. The derivative is continuous. Let's say at 2. Therefore, F must be, let's actually say the derivative exists at 2. Let's just say it. Doesn't the derivative exist at 2? There's a point there. And the derivative can't exist at 2 if F is not continuous. F must be continuous at 2 and 4. All right? D is an interesting choice. What does somebody who chooses D think of? Very common misconception. Yeah, they weren't looking for the antiderivative graph. They took the derivative graph. All right, they took the derivative of the derivative. This actually would be the second derivative. All right, cool. Let's go on to piece. Is that all for that slide? Is that all for that one? Is there? Okay, cool. All right. This is a pretty common mistake, or not mistake, common problems, short answer or multiple choice problem, where you're supposed to make a piecewise beautiful. All right. You're really working on two levels here. You are working with continuity, which for these purposes, it helps to just think left hand, right hand, and the point have to all be the same for continuity. And the slopes must match. Would you write yourself a note here? For differentiability, this is really saying no sharp turn / change in slope. It can't be the case that the slope from one side is this, but then all of a sudden, boom, it goes to something else. The slopes must smoothly transition, smooth transition. Write the keywords locally linear. All right. The issue is not, hey, the slope was -1 on one side and +1 on the other. If the slopes smoothly transition between. The problem is if the slope goes from -1 to +1, just like that, then there's a problem, because if you zoom in on that, no matter how much you zoom in on that, that's not a smooth slope transition. It's not locally linear. All right. So if you get a problem like this, we're trying to make the narrow parabola, 3x squared, meet the line ax plus b, so they have to first of all meet at 2, so that would mean the line has to be just right, and it must be the case that the line has a smooth transition of slopes, so the slope blends in. That would have to be a pretty special A and B to make that all come true. That's the question. Make it so this is continuous and differentiable at the point we're going to start with continuity. I do not want you to just throw around work. So I don't want 3x squared equals, I want good calculus with limits. The limit, as x approaches 2 from the left, uses the function 3x squared. The limit, as x approaches 2 from the right, uses the function ax plus b. Now, if we evaluate each of those limits at 2, where does the parabola leave off at? When x is 2, the y value is all the way up to 12. The parabola leaves off at 2, 12. Now we need the line to meet it there. At 2, the line equation is 2a plus b. Now certainly that's one equation, 2 unknowns, so we're not going to solve that alone. We need more. That's where the differentiability comes in. It must also be the case that the derivative from the left, which is 6x, has to equal the derivative from the right so that the slope's match. What's the derivative from the right? B, A, okay. At 2, what's the slope of the parabola? At 2, the parabola leaves off with a slope of 12. That means our line slope, which is A, has to be 12 when they meet. If A is 12, I just need to get the right B to make sure the lines meet. So going back to the continuity, that implies that the B would have to be negative 12. That's a line that would, first of all, meet the parabola at 2, and second of all, match the slope of the parabola at 2. You with me? All right. Try that one on your own then, please. Showing good work with limits. What do you say A is?
I hope you did good work. Ax squared equals the limit for continuity.
Something like this. That implies that A equals negative 2 plus B. From continuity, from differentiability, did you get that the limit as x approaches negative 1 from the left is 2ax, and that equals the limit as x approaches negative 1 from the right, which is 2. So what? Negative 2a equals 2. So a is, and b is 1. Yes? Success? Okay. Try that multiple choice. It's pretty common AP style. Try that one, and we'll go over the hardest part after that. Okay, what do you say here? First of all, if f has a limit, then the left-hand, right-hand limits, the one-sided limits must equal, yes? Aren't the one-sided limits both using this, though? And as x goes to 2, what is the limit from both sides, right? So is A true or not? It is true. Okay, it's true. It uses the same function. But what about continuity? Continuity is there's a hole at 2. Did they fill the hole? And do you say yes or no? No, the limit as x goes to 2 is 4, and they put the dot at 1. That's a problem. The limit from the left and the right is not equal to the point, and therefore that is false. Therefore, do I need to even think for 1 second about 3? No. If it's not continuous, it can't be differentiable. It must be the case that it's 1, 0. You follow? Okay. Last but not least, this is the part that tends to give students any trouble, if there is trouble. Using the definition of the derivative to prove that the derivative doesn't exist at a point. Right? You know the derivative of f of x equals the absolute value of x minus 2 does not exist at x equal 2 because there's a sharp corner there, or a corner there. Prove the derivative doesn't exist using the definition of the derivative. Okay? So, let's be 100% clear. Every time I give this on the test, there's a subset of people that says f prime of 2 doesn't exist because there's a sharp turn there, because corner there. Is that true? Sure is. Did you answer the question in any shape, way, shape, or form? You sure didn't. I told you the derivative doesn't exist because of the corner there. I got that covered, okay? I want you to prove to me that the derivative doesn't exist. Prove it using the alternate definition of the derivative. All right, so you need to, starting with the alternate definition, say why doesn't the derivative exist there? Prove it doesn't exist. Now remember the definition of the derivative, the alternate definition is something like f at x minus f at a, which in this case is 2, over x minus a, which again in this case is 2, as x goes to 2. Now, more important than just writing meaningless symbols down, let's remember the concept. The idea on all derivatives, even after all your product rule and all that knowledge, is still the idea of finding the slope between 2 points and then saying what happens as the points get closer and closer and closer together, approaching this tiny little triangle that represents slope at 1 point, all right, which is really theoretically not possible. The idea then looks something like this. Now this represents the slope. That's the slope between 2 points. That's secant slope. This is what accomplishes the two getting closer together. Now, this whole thing, though, is predicated, my picture here seems to imply that x has to be on the right. And x could be on the right. X could be approaching 2 from above. As you write yourself a note, look at one-sided limits. If I wrote this, that's actually, I'm running out of space, so I'm going to go, what is the function here? What is f of x? Absolute value of x minus 2. What is f at 2? 0 over x minus 2. All right. Now this then becomes the rather well-worn, many times done, absolute value limit. Okay, we've done this, I bet, 10 times at least. All right? Now it's 0 over 0, surely, and algebra fails you because of the absolute value. They're not equal. I can't divide them out. Instead, think numerically. If x is 3, then what do I get? 1. If x is 2.5, what do I get? 1. If x is 2.001, what do I get? 1. Okay. Basically, for positive x's, the absolute value, or x is greater than 2, does the absolute value do anything? No, these are exactly the same. Those always come out to be 1. That's totally justified on the right-hand side. Aren't those slopes 1? Okay, so let's consider the left. As x approaches 2 from the left, well, say at 1. What's the absolute value of 1 minus 2? 1 over 1 minus 2. Negative 1. Okay, see, these the absolute value is doing something. It's taking a negative, making it a positive there, but not in the bottom, so these always work out to be negative one, which also matches my picture. Now that is why a sharp turn is bad, because the one-sided limits of the slopes aren't the same. And we know that if you ever have a limit where the one-sided limits aren't the same, then all bets are off. The limit doesn't exist. So because negative 1 is not equal to 1, the two-sided limit does not exist, and we conclude then that f prime at 2, which is the two-sided limit, does not exist. Sharp turns are bad because the slope goes straight from one to the other, which means a violation of the one-sided limit. All right, try one on your own. Actually, in the interest of time, I'm going to tell you it is continuous. Just show it's not differentiable at x equals 4. It is continuous, okay? I'll tell you, it is there. All right, let's just focus on the differentiable part. Using the definition of the derivative. If you have your phone out, please put it away because I am attending the test back. You may not have your phone out for the test and stuff. Okay, let's talk about that, and we'll be good to go. So, I don't enjoy getting this on a test because it takes me a while to grade. But I would expect you to be something like
G prime at 4 is the limit as x goes to 4 of
f of x minus f at 4 over x minus 4. Basically stating, hey, I'm using the alternate definition of the derivative. Then going one-sided limits, and feel free at that point to use more specifics. If you approach 4 from the left, then the function is x squared plus 2. F at 4, what is f at 4? 14? Are you with me? Okay, over x minus 4. That'll always, if you did this right, every derivative should always be 0 over 0 because it's trying to take difference between those two infinitesimally small. So you're going to have to do a little bit of algebra. In this case, if you factor and cancel out, you should get that the left-hand slope is approaching 8 as they meet, yeah? Do you agree? I'm not hearing a lot of agreement. The right-hand side is the function 4x plus 2. That's a little different algebra. It obviously also is 0 over 0, but there you can factor out a 4 and drop the x minus 4 out. That's 4, and therefore you have shown that the left-hand slopes and the right-hand slopes are not the same. So G prime at 2, you could say the one-sided limits are different, but basically at that point you could say G prime at 4, not 2. G prime at 4 does not exist. Just so we're 100% clear, there's always somebody, I know there's somebody in this class thinking, that's not the way I did it, but I'm sure I'm fine. Let's be very clear. I'm going to say it abundantly clear. If you said the limit as x goes to 4 from the left is 2x, and that's not equal to the limit as x approaches 4 from the right, which is 4, that isn't it. That is not using the definition of the derivative. That's using the power rule. That is the shortcut I would use on a multiple choice question to answer the question here. That works fine there. It is not a proof. It is not using the definition of the derivative. It won't do. At most, it would get you 1 out of 5. At most. That won't do. Is that 100% clear? Good. Okay. This is what it should be. That's a proof by virtue of the definition of the derivative. Okay, let's look at the test, which I am now going to stop this recording.